So land use change is incredibly important in terms of the amount of carbon that's being emitted to the atmosphere. It accounts for about 12% of all anthropogenic emissions, but that doesn't count the emissions that come from non-anthropogenic sources. So wildfires and natural disturbances are also releasing carbon into the atmosphere. The flip side of that is how much carbon is being taken out of the atmosphere by land use change. So we've got forests that are recovering, particularly in Europe and North America, from agricultural areas that have been abandoned. And those areas are sequestering carbon, or taking it out of the atmosphere and putting it into woody biomass and transferring a lot of it to the soil as well, particularly in high northern latitude regions. So it's a huge amount. Even though 12% of those emissions that go into the atmosphere are from land use, land cover change, we've got a lot that's actually being drawn out. It's just being offset by how much we're releasing. We have ways of quantifying how much has changed using, for example, bookkeeping methods, where we have reported figures on how much biomass was harvested or how much area was cut. But we need additional measurements to reduce the uncertainties. So we use remote sensing in a number of ways to be able to look at wholesale land use change, areas like clear cuts, areas that are very easy to identify from remote sensing. We can also look at areas that are suffering from degradation, so trees that are dying more often in stands that are generally otherwise healthy, or selective logging where individual trees are taken out, but that's much harder to do. We can also use remote sensing not just in that sense from a bottom-up perspective, but also a top-down perspective. So we can look at carbon concentrations in the atmosphere and trace them back to where they came from originally. So you have two independent measurements then of how much carbon was emitted.
I'm going to look at the next stage of going from an indirect measurement to something that we can actually quantify. So if we move from this rough estimate of vegetation to a property called net primary productivity. So this is data from the same set of satellite observations that I showed before, but now we've transformed the satellite observations into something that tells us about how much carbon is being grown and stored in different parts of the Earth at different times of year. It's the amount of carbon per unit area per unit time. How much carbon is being absorbed and stored by vegetation on the Earth's surface over a given time period, typically a month or a year. And here again, we're following it through multiple years from 2000 to 2014. Perhaps not surprisingly, where we saw that there was lots of vegetation before and where it was really dynamic, we're seeing lots of net primary production. Now, the critical thing about net primary production is that when we refer to net primary production in agriculture, that's the bit that we get to eat, that we get to turn into animal feed. It's the bit that's the commercially useful bit. So net primary production is something that we have of a great deal of interest in, and a great deal of interest in being able to understand how it's responding to changes in climate and to changes in management. So the question is how do we go from this measurement of reflectance in different parts of the spectrum into this property here, which is how much stuff is growing and being stored on the Earth's surface in the form of vegetation. The way we do that is by going through a process of modelling. It's the only way we can do it. What we have to do is we have to develop models of how vegetation grows and how it stores carbon and how it photosynthesizes, and ultimately how it absorbs solar radiation and how it reflects some radiation. And if we have a model that can do those things, then we can take an observation of how much sunlight is reflected in different parts of the spectrum, and we can infer from that observation what the properties of that model is that are giving rise to those observations. So it's this link now between observations and models of the Earth's surface that allow us to take a measurement which fundamentally we're really not interested in many respects, a measurement of photons at the top of the atmosphere, and we can turn it into something that has very, very high value, both in terms of understanding how the Earth system is changing and how we're interacting with it and what our management options are and how we can control it, how we can respond to it. A related and important property of the land surface is the albedo. Now, the albedo of the Earth's surface is simply the reflectance. It describes how much of the sunlight arriving at the surface is reflected back into space and, of course, is available to heat up the atmosphere or is absorbed to heat up the surface. So this is a satellite-derived map of albedo over the Earth's surface. This is for 1998. And again, we see this changing subtly over the course of the year. This is in the Northern Hemisphere summer in June, and we can see the advance and retreat of the snowfields and how bright they are. So this brightness of the Earth's surface is a very important parameter for climate modelling because it controls the amount of radiation that's absorbed at the land surface. So it's what the climate modelers call their lower boundary surface condition. And this is a product derived from European Space Agency data in response to the interest in essential climate variables which are monitored over long periods of time, sufficiently long that they can be used to test and parameterize and validate climate prediction and numerical weather prediction models. So this was part of an ESA project to take data from multiple different satellite sources and integrate them all together to provide our best estimate of albedo of the Earth's surface. Just as critical to a data product like this is the uncertainty. A value of albedo without an uncertainty is a very difficult thing to use, and in some respects we have to kind of move beyond just looking at the values themselves. The uncertainty will have knock-on effects when you use an albedo product in a modelling system, and that's something that we're recognising more and more in the satellite observation community, is that the values of these products themselves are enhanced dramatically if we can include realistic estimates of uncertainty and explain to people who are using these observations what those uncertainties mean. One of the things I want to look at now is one of the more sort of dramatic aspects of the Earth system, and that is fire. Now, this is a series of global observations made in the thermal part of the spectrum. So the things that I've focused on up until now have been in the visible near-infrared part of the spectrum. But fire is clearly a major part of the Earth system in terms of as a driver of change. What we see worldwide these days is that the majority of these fires are man-made. In Africa, it's estimated that something like 99% of the fires that occur in Africa are man-made. And clearly, fire has a big impact in terms of removing vegetation and changing the nature and structure of vegetation that's there, but it also has broader implications for us. If we look at fires in Southeast Asia, for example, we're well aware of how these large-scale forest fires that are often caused by logging and land clearance can run out of control and can send huge plumes of smoke across vast areas of Southeast Asia, which in turn cause very, very serious health problems and respiratory illnesses and large numbers of deaths in many cases. So we can make observations of fire from satellites in terms of the thermal part of the spectrum. And this is another part of this whole equation of trying to understand how vegetation and how the broader biogeochemical cycles are changing in response to our interaction with them. These particular observations are collected from the NASA MODIS instruments on board the Terra and Aqua platforms. But there are a number of other satellites that make observations in the thermal part of the spectrum. We're familiar with the Meteosat-style weather forecasting satellites, which also observe in the thermal part of the spectrum. So these geostationary satellites are now often used for these kind of thermal observations that tell us about the range and activity of fire. In the future, we're moving into an era where new satellite sensors are going to be launched, particularly by the European Space Agency as part of the Sentinel program, that will augment these kind of observations and provide finer time and space scale observations of fires over the globe. And this understanding of how fire changes vegetation into aerosols and gases and soot and dust is a very important part of understanding the climate interaction between the carbon cycle and our cells.